Okay, so this is gas ion half cells, and in particular we're going to look at the hydrogen half cell. That's an important example. So here's the half equation for the hydrogen half cell. H plus an electron goes to half H2, and this will of course be a gas. Hydrogen is a gas at room temperature and pressure. And then I've also given you the electrode potential value. This is the only electrode potential value you need to memorize. And it's not hard, it's 0.00. The reason it's that is because we set the hydrogen half cell as our reference. Every other half cell is a comparison to the hydrogen half cell. So by definition, the hydrogen half cell is 0.00. Okay? And as this involves a gas, let's add on our state symbols, and of course the positive ion will be aqueous. This is going to look slightly different to the half cells we've seen so far. So what we do is we have our ion in solution, as it always will be. If this was the standard hydrogen half cell, it will be 1 mole per decimeter cubed. We notice in our equation there's no solids, so just like if we had an ion-ion half cell, we're going to need to make the electrode out of platinum because platinum is inert. And then we have this extra thing here. This is supposed to represent some kind of glass casing, and it has to be sealed apart from one entrance here and then an exit out the bottom. So don't be putting any holes at the top there for the wire. And the reason for that is what we're going to do is pump in some hydrogen gas through here. And again, if it was under standard conditions, we'd need 298 Kelvin and 1 atmosphere. So if I lift a little hole there, all of the hydrogen gas is just going to escape out the top. As it is sealed, the hydrogen gas will get pumped along here, forced down, and it'll bubble through this solution. So you'll get bubbles of hydrogen gas bubbling through and hitting the electrode. So what's going to happen at the electrode? Here's one I made earlier, Blue Peter style. So either your hydrogen gas will hit the electrode, it will lose an electron, and it will change into H+, or the reverse can happen and H+ can pick up an electron to become, well, half H2 if this was balanced. Okay, so we've got this reversible reaction going on there. Now, why is the hydrogen half cell really important? It's because we can use it to find the electrode potential of other half cells. We said, almost by definition, the hydrogen half cell is 0.00 because it's a reference. So if I was to connect the hydrogen half cell to another half cell and measure the E cell on a voltmeter, and let's say I got, I don't know, minus 1.27. Well, as the hydrogen half cell is 0.00, that tells me the electrode potential of the other half cell must be minus 1.27. If this came out as, I don't know, 3, then the other half cells must be 3. Okay, so important points to remember: how to draw a gas ion half cell. And I've given you the example of hydrogen. The fact that the hydrogen half cell is a reference, and so therefore a standard, and so therefore will have a value, an electrode potential value of 0, and how we can use the hydrogen half cell to find the electrode potential of another half cell just by connecting it up to it with a voltmeter. And then whatever the voltmeter reads, that is the other half cell. Boom.